Good morning everyone. So in the earlier classes we discussed about the manufacturing of various polymer matrix composites. So it depends upon the profile of the component. We have used various processes, that is hand lay process, spray lay process, vacuum bagging, pressure bagging, autoclave, automated and filament winding process. So in the last class we discussed about automated tape process and filament winding process. So to produce an hollow sections, we are using filament winding process. By means of filament winding process, we can get cylindrical hollow section or conical sections. So it means oval shaped components. So depends upon the profile of the component, we have used various manufacturing methods. So similarly, today we are going to discuss about Pultrusion process. So Pultrusion process is similar to extrusion process. So the only thing is, here in extrusion process it is coming out of the component, whereas in Pultrusion process we are pulling the component. So here in the die itself, the matrix and fibers are mixing together and we are pulling the materials from the die, so that the process is called Pultrusion process. So this is a Pultrusion process. As we discussed that Pultrusion process is similar to extrusion process. So it is similar to extrusion process. But the thing is, here the workpiece is pulled through the die. So whereas in extrusion process it is extracting from the die. But here in Pultrusion process, if this is the die, we are pulling the component. That is in Pultrusion process. Next, like extrusion, Pultrusion produces continuous straight sections. So Pultrusion process, by means of this process we can get continuous cross section profiles like pipes, tubes, channels and all. So these are the various components that can be produced by means of Pultrusion process. So if we observe the cross section of the component, the cross section is uniform throughout the length. So if we consider here a U-shaped component, throughout the length it is having same cross section, whereas here it is a square channel. So throughout the cross section it is having same. So similarly circular as well as L-shaped, V-shaped. So different types of components. If we want the same cross section of components, then we will go for Pultrusion process. So like extrusion process, Pultrusion produces continuous straight sections of constant cross section. So as we discussed that if we want the same cross section throughout the component, then we will go for Pultrusion process. This is economical compared to the earlier processes. So this process is developed around 1950 for manufacturing of fishing rods. So initially first this was produced for manufacturing of fishing rods. So as you know that the rods are having uniform cross section. So by means of this Pultrusion process we can produce a solid component or a hollow component. Both the components can be produced. So this was first introduced for developing of fishing rods in 1950, which was made up of glass fibers, reinforcement polymer. So this is the working, this is the construction of Pultrusion equipment. So here we are using a straight fibers. So directly by means of racks. So here it consists of two racks, that is fiber racks. By means of fiber racks, we are extracting the fibers. So in this process, we can use the fibers or the fabric also. So it depends upon the application of the component. We can use a different oriented fabric, or directly we can use straight fibers also. That is from the creel or bobbins or rovings. So here it consists of racks. On the racks, we are having n number of creels. So number of bobbins, from each bobbin number of fibers are extracted. So on the top and bottom layer, for good surface property, we are adding cloth on the top surface, so that the fibers will not come out of the cross section, it will come out of the component, and then the surface finish is good on both the surface to get the desired structure, texture. So we are using cloths. By means of cloth racks, we are extracting the cloths. So it consists of fiber racks and then cloth racks for handling clothes. These are the 4 clothes. So after that, so here it consists of a preheater. So if there is any moisture or foreign particles on the fibers, those will be vaulted in these preheaters. So similarly, to maintain some good bonding between the fibers and matrix material, here we are preheating the fibers so that any external materials or foreign materials can be escaped from the fibers as well as, so those will give good bonding with the matrix material. So after that, it consists of a polymer injection. So it consists of a pressurized resin tank. So as we know that our composites consists of a fiber, it means the reinforcement and matrix material. Here reinforcement is coming from this direction, whereas matrix is stored in a pressurized tank. So this pressurized tank, those matrix is influenced in this die. So this is the complete die. So in the die, the matrix is impregnated onto the fibers, so that we are getting a composite with a defined matrix. Here the die consists of the mixing of this reinforcement and fibers, along with that the cross section also. The cross section can be achieved by means of this die. So if we want a square shaped rod, complete solid square shape, then the die should be similar to that component. So if we want a circular, then the die cross section should be a circular. So it depends upon the profile cross section, we are going to use the dies. So again, at the same die, here we are having heaters. At the end of the die, we are having heaters, so that the consolidation will take place. So due to heating of the component, it means the matrix and reinforcement, our consolidation or the polymerization starts and it solidifies. So next, so as we discussed that, so this is the mixing. Till now we are gathering the reinforcement and matrix together and we are forming a section. So from now onwards, we are pulling the component. So by means of hydraulic rams, we are pulling the component from the die by means of this two engage. So this is one and this is two. By means of this hydraulic rams, two rams, we are pulling the component. Those are called pulling mechanism. So here we are pulling the component. After that, by means of a cutoff saw, we are cutting the component to a required length. So these machines are used to produce continuous cross sections over a length. It means over kilometers of length it can produce, but depends upon the application. By means of this cutoff saw, we are going to cut the cross section. Depends upon our required length. So finally, after cutting, we are getting a finished component. This is our pultrusion process. Now we will watch a video. So pultrusion process. So fibers pulled from a creel. So as we discussed that the fibers are extracting from a creel. So this is the creel. So fibers pulled from a creel passed through a resin bath. So here it consists of a resin bath. And then through a heating dye. So here itself the component consists of heaters as well as the shape of our component. So both the things are available here, the resin bath as well as the heater through a heated dye. Next, dye completes the impregnation of the fiber. So it completes the impregnation of the fiber with matrix. So the matrix is none other than the resin. So here the pressurized resin tank. So this is our matrix material. So our fibers are impregnated with the matrix material. It controls the resin content. So as we know that the dye contains different cross sections. So those dyes are controlling the matrix material. Controls the resin content and cures the material. So it controls the resin content and cures the material into final shape as it is processed through the dye. So after passing the dye, we are getting the final shape of the component. So cured profile is then automatically cut to length. So as we discussed, so depends upon the required length, the cured resin or cured component is cut into pieces. Next, fabrics may also be introduced. So fabrics may also be, so regular fibers can be used. So this is a fiber rack. So fibers can be used or fabrics also. So fabrics or fibers. So depends upon the application, we can use fibers or fabrics. So if we use fabrics, the cost of the secondary process is high. Why? Because the fibers should be arranged in a zigzag manner. Depends upon the application. Those can be obtained in different orientations. So fabrics may also be introduced into the dye to provide fiber direction other than at 0 degrees. So as you know that depends upon the fiber orientation, the property of the component varies. So to get the desired property, we are arranging the fibers in other directions other than 0 degrees. That can be possible if we use fabric materials. Next, material options. So resins, any type of resin can be used in this process. Examples, epoxy, polyester, vinyl ester, phenolics. Any type of resin can be used in this process. So fibers, any type of fibers can be used in this process, like glass fibers, Kevlars, carbon fibers, and its different orientation and different GSM can be used in this process. Next, cores. Generally we are not using any cores. Generally core is used for obtaining desired thickness. So to get the desired structure. So here the cross section is obtained by means of the dye itself. So here we are not using any cores. Next, advantages. So this is very fast. The process is very fast and economical way of impregnating and curing materials. So compared to earlier process, here we are using heaters, so that the consolidation is very good. It takes very less time, so that it is very fast and economical way of impregnating and curing materials. Next, resin content can be accurately controlled. So by means of the dye surface, depends upon the dye thickness or its diameter, we are controlling the matrix material. So resin, matrix or resin. So resin content can be accurately controlled. Next, fiber cost is minimized since the majority is taken from the creel. So here we are not using any secondary operation. Secondary operation in the sense of braiding or woven things. So different orientations can be obtained if we use any fabric. So here we can use the fibers, directly fibers from the creel itself. So the fiber cost is less. Next, very good structural properties of laminates, because the profiles have very straight fibers and have fiber volume fraction and high high fiber volume fraction can be obtained. As we know that here our composite consists of fibers, as it means reinforcement as well as matrix. So matrix content can be controlled by means of die, so that high fibers can be obtained. So if we want 10% of matrix material, we can get that, depends upon the die. So if we want 90% of fibers, the same thing, we can achieve that. So it depends upon the required property, we can control the fibers or matrix. So due to controlling this matrix, high fiber content can be available, so that high mechanical properties can be obtained. Next, resin impregnation area can be enclosed, limited to volatile emissions. As we know that the complete impregnation is doing in a closed chamber. So in this polymer injection is in this section, complete the fibers and matrix are mixing together. So it's a complete closed chamber, so that no reactants are coming out from the chamber. So it's a good health and safety issues. So good for health and safety. So the same thing, resin impregnation area can be enclosed, so that limiting to volatile emissions. There are no volatile emissions. Next, disadvantages. Limited to constant area. So limited to constant cross sections. Only same cross section can be achieved throughout these sections. Next, heating dies costs be high. So as we know that here we are using heaters. So due to usage of these heaters, the cost of the manufacturing method or this process is high. Next, applications. So generally these are used for beams. So as we know that beams are having constant sections. So due to that, these are highly used for beams, grids. Grids are used in roof structures, bridges, ladders, and frameworks. So these are the various cross sections of our pultrusion process. So as we know that, as we observe that here we are having various cross section profiles. So all are having uniform cross section throughout the length. So here by means of this we can produce various components. So similarly, if we observe the various components also, here we are having a circular solid one. This is one circular solid, and this one is circular hollow section. And here it is a square type. Here it is L shape, rectangular shape. We can produce a solid as well as hollow sections. So both the things, closed mold or open frame or open shapes can also be obtained in this process. So these are the various applications or various profiles of our pultrusion process. Next one is, so till now we discussed about open molding process. So as we know that open molding process is done by means of a single die, so that only one surface finish is good. Finish of one surface is only good. So if we want the surface finish to be good on both the sides, then we will go for closed mold process. That is this one, closed molding process. So performed in molds consisting of two sections. So till now we used only one section, that is only one die. On the bottom we are using the die, on the top of that we are adding layers. So now if we want surface finish on both the sides, we need to use two sections. One is open one and the other, one is bottom die and the other is top die. So by opening and closing the dies, we are getting the components. Next, tooling cost is more. Tooling in the sense, our dies. The cost of the dies is high. Why? Because here we are using two dies, open die and top die and bottom die. Two dies to be closed. So earlier we used only one surface. So compared to that, here the die cost, it means that tooling cost is high. Tooling cost is more than twice the cost of open mold. So in open mold we used only one, whereas here in the closed mold we are going to use two dies, so that the cost of the tooling, the cost of these dies are high. It is twice than the open mold process, due to more complex equipment required in this properties. So complex in the sense that two dies. Next, advantage of a closed molds are good surface finish on all part surfaces. So whereas in the open mold, we can get only one good surface. So here, all parts, it means if the compound is having n number of sides, all the sides can be a good surface finish. Higher production rates. So the process can be fast in this closed mold processes. Closure control over tolerances. So accurate dimensions can be obtained. Why? Because two dies are closing together, so that the gap between the dies can only be the size of our part. So that closed dimensions, closed tolerances can be obtained by means of this process. Next, more complex 3D shapes are also possible. So by means of this closed dies, we can get a different cross-section profiles also. Next, so these are the various types of open mold processes and closed mold processes. So in the earlier classes we discussed about open mold process. So in matched die are also called as closed die process or closed moldings. So here we are having various, that is RTM, resin transfer molding, as well as compression molding, sheet metal. These are the various manufacturing methods of our composites. So now we will discuss about RTM, that is resin transfer molding. So as we know that it consists of two dies, that is the bottom die and the top die. So initially we are going to take dry fabrics. So dry fabrics in the sense dry reinforcements. So those reinforcements, so these are the two parts. So this is the die 1, this is the die 2. It means top die and bottom die. So first we have to separate both the dies, and then we have to place our fabric. This is the dry fabric onto the surface of our mold. So if it is a regular surface, straight surface, we can directly place our fibers onto the surface. If it is having some cross sections, some shaped things, then we need to press the reinforcement into that shape and we have to transfer onto the die for easy impregnation as well as easy sitting of our fibers. So after placing our fibers onto the die, so we need to close that die. After that, now the third step is resin injection. At this stage, we are passing our reinforcements onto the, we are pushing our matrix material onto the reinforcement. It means impregnation takes place at this stage. The next one is resin curing. So it depends upon the type of the resin. Here we are going to supply heat. So already we are supplying the pressure. It means in the two dies. So in between the two dies, some amount of pressure is created. So now depends upon the matrix material, we can supply heat also. After that, if we allow for certain time, the material will cured. It means the polymerization takes place and consolidation takes place. So that after the final step is ejecting. So two dies are separated and then the component is ejected from the pot, ejected from the mold. The same process can be repeated for n number of times to get n number of components. So this method is suitable. Closed dies are suitable if we are going for mass production. If the component manufacturing is high, the number of components are to be high, then only we will go for this closed molding process. Why? Because the cost of the tooling is high in this closed mold processes. Next, resin transfer molding. So here, fabrics are laid. Now we are discussing about the process. So fabrics are laid up as a dry stack of materials. So without any impregnation of matrix material, dry surfaces, dry fabrics are used in this process. Next, fabrics are sometimes pre-pressed. So sometimes pre-pressed to the mold shape and held together by a binder. So sometimes, so depends upon the shape of the component. So the reinforcement should be in that particular position. To maintain it is in its particular position, those are pressed, and we can use binders also to get the desired shape. Next, these preforms are then more easily laid into the mold. So if those are not pressed, those will be in different shapes. Those will occupy different shapes. To maintain its original shape, we are pre-pressing. We are pre-pressing those fabric materials. Next, A second mold tool is then clamped over the first and resin is injected into the cavity. So this is the third step. So the second mold, both the molds are placing together and the resin is impregnated or passing through the fabrics. Next, once all the fabric is wet out, the resin inlets are closed and the laminate is allowed to cure. So after a proper amount of matrix is injected, then we are going to close the walls and then we are allowing the component to cure. It means for polymerization. Next, both injection and curing can take place at either ambient temperatures, normal temperatures, or at elevated temperatures. So it depends upon the type of matrix. The process can be done at ambient temperatures or at elevated temperatures. So let's watch a video.
The basic RTM process involves injecting a resin through reinforcement placed in more substantial rigid tooling manufactured from composites or metal. RTM can offer distinct advantages, particularly if temperature-controlled tooling is used. Increased productivity through the use of higher injection pressures and heated molds. Improved quality. Improved product consistency due to better process control. Improved dimensional tolerances. The mold is gel-coated by either hand or spray application. Because of the use of heated tooling, the reinforcement can be laid onto the gel coat far quicker than at ambient temperatures. A surfacing veil or fleece material, as shown here, can be used to reduce the glass print-through. Once again, deformable stitched mats, such as Rovicore, offer distinct advantages in glass loading. Core materials may be incorporated, but their dimensional accuracy is critical to the success of RTM. The mold is closed and clamped using bolts, toggle clamps, or sometimes a press. Liquid heating is used to ensure consistent temperatures. 40 degrees C is a typical mold temperature. The mold is vented at the point of final fill. Resin is injected from a central point at typical injection pressures of between 2 and 4 bar. Machine options such as the mold pressure guard or MPG ensure that the injection is controlled and that the molds are not overpressurized. It would be expected to see a small amount of resin at the vents to ensure that the mold is full. Once injection has been completed, the injection head is removed, a stopper is placed in the injection hole, and the machine flushed with solvent. Once the resin has cured, the mold is opened and lifted to allow demolding. The heated tooling allows quicker curing of the resin, and so quicker cycle times are achievable when compared with ambient temperature processes. RTM can use metal molds such as nickel shell, aluminium, or steel for maximum durability and improved surface finish. However, the principles of the mold design and the process remain the same. Further automation can be achieved using auto-sprue technology. This valve is built into the mold and allows simple connection of the injection machine. At the end of injection, the auto-sprue automatically flushes the machine with solvent, and then the machine can be easily disconnected. Once the part has cured, then it can be demolded, leaving the mold ready for the next component. The use of RTM can be limited by the higher cost of tooling, the cost of an injection machine, but also by the gel time required for mold filling, which limits productivity in very high volume applications. However, RTM is now a proven technology for fast and efficient production of GRP components.
based upon the means of transferring. So as we know that, so we are transferring the matrix material onto the reinforcement. So based upon the type of transferring resin to mold, transferring resin to mold. So it means by means of pressure or by means of vacuum or by means of resin infusion. By means of various methods we can pass the matrix material onto the reinforcements. So it depends upon the passage of our matrix material. Those are classified into various types. That is RITM, VARTM, SCRIM, WIP, etc. So these are the various methods that depends upon the type of infusion of our matrix material. So if the resin is infused into the mold cavity, then it is known as resin infused transfer molding. So in the earlier case we see in that RTM, so there resin is transferring. If the resin is infused, then that is called RITM. So this is the schematic of our process. This is the schematic of our process. Here, by means of one inlet, so here the mold, this is the bottom half and this gray color is the upper half. So in between these two dies, the cavity is going to be filled. So here this one is our reinforcement. So the reinforcement is impregnated with the matrix material. Here we are pushing the matrix material onto the reinforcement. So here that is called RITM, resin infused transfer molding. We are infusing the we are infusing the matrix material. Similarly, one more process. If vacuum is applied to the mold cavity to assist resin, so here earlier we passed the resin material, we pushed. So now by vacuum is used to suck the resin from the resin, then that is called vacuum assisted resin injection process. So this is the schematic of this process. So here by means of this vacuum pump, we are dragging the resin material from the bath. So here it consists of a resin bath. On the other side, here on the side it consists of a resin bath. On the other side it consists of vacuum pump. So here by sucking the pressure, the air, the resin is coming into the chamber. It means into the cavity. So here by means of vacuum we are passing the we are passing the resin material. So there by means of vacuum pump we are sucking so that the air is moving towards this vacuum pump. So here the air is sucking the resin material. So that by means of vacuum we are using this process. Then that is called vacuum assisted resin injection molding. Let's watch a video. Next, advantages. So by means of this process we can get high fiber volume laminates. So it means high fiber volume laminates can be obtained with very low void contents. So high fiber volume can be obtained by means of this process with very less voids. Next, good health and safety. Why? Because the complete process is done in between a closed die. So in between the two dies, so that the impregnation, the complete reaction takes place inside that die, so that no volatiles are coming out of the chamber. So that it is very good for health as well as for environment also. Next, possible labor reductions. So here we are not going for the process like hand lay process. So manual interference can be reduced so that the labor costs also reduced. So both sides of the compounds have a molded surface. It means both the surfaces. So if we are if we use this closed die, then both the surfaces, top surface and bottom surface of the components can be can have a good surface finish. So if this type of components are manufactured by means of this closed process, we can get good surface finish. It means if we go for this automobile parts, then the top surface can also have good surface finish, and the bottom surface also can be good surface finish. Similarly, these blades, propellers and all, so those all can be manufactured by means of this closed dies. Next, disadvantages. Matched tooling is expensive and heavy in order to withstand pressures. So the tooling cost is very high, is expensive. As we discussed that here we use two dies, the bottom surface and top surface, so that the cost of these dies are high. Next, generally limited to small components. As we discussed that if the size of the component is high, then the tooling cost will also be increased, will also be high. So to reduce the cost of our fabrication, we are using only small parts by means of this process. Next, unimpregnated areas can occur, resulting in very expensive scrap parts. So if this is our component cross section. So here initially we place reinforcement materials. After that we are passing our resin material. It means matrix material. If any unfilled sections, if some amount of this section is not filled, after ejection we can identify the component is unfilled. If we identify at this stage, the cost of our fabrication is very high. Till the time we spend much time as well as money for producing the component. At the final stage, we are obtaining a wrong product. So due to that, we are getting an expensive scrap. So that is resulting in very expensive scrap parts. Next, material options. So resins, any type of materials, mostly epoxy, polyester, vinyl ester, phenolic materials can be used in this process. Although high temperature resins such as bismuths can be used at elevated process temperature. As we discussed that this process can be done at ambient temperatures as well as at elevated temperatures. So high temperature resins can also be used in this process. Next, fibers. Any type of fibers can be used in this process. Coarse, not honeycombs. So as we know that honeycombs are hollow in section. So if we use honeycomb sections, hollow sections, then the cells would fill with the resin and the pressure involved can crush some amount of cells or the foams. So we are not using a very general course for this process. Next, applications. So these are the various applications for producing automobile body panels. So this is one of the example for that. So automobile body parts. So similarly, truck air deflectors, wind blades, solar collectors, propellers, bathtubs. So wherever we require the surface finish to be good, then we will go for this process. Similarly, these are the various applications of our process. Next, process selection. So several factors. So till now we discussed about the various processes, that is hand lay process, spray lay process, autoclave process, pressure bagging, vacuum bagging, automated tape process, filament winding, pultrusion process, as well as the finally resin transfer molding process. So whatever the process it is, so prior to the selection of the process, we need to identify these steps. So several factors should be considered before selecting the manufacturing process. So before selecting the process, we need to identify several factors. That is the materials. What are the metals we are going to use? What are the types of reinforcements? What is the matrix metal we are using to produce that component? Next, reinforcement architecture required. So whether we are going to use a braided fabrics, the reinforcement direct straight fibers from the creel or the fabrics, whether it is woven or braided. So that also plays an important role. Next, complexity of part geometry. So depends upon the complexity, we are having various methods. If the complexity, it means if we are going for simple components, then we will use hand lay process. If it is having some complex geometry, then we will go for closed mold process. So depends upon the complexity, we need to select our process. Next, number to be manufactured. So again, how many number of components to be manufactured is also an important part. The finally, how much time, how quickly they are to be manufactured. So how much time required for curing is also plays an important role. So these are the various methods for manufacturing of polymer matrix composites.